Hi, and welcome to section 7.1, What is a sampling distribution? By the end of the section, you should be able to distinguish between a parameter and a statistic. Use the sampling distribution of a statistic to evaluate a claim about a parameter. Distinguish among the distribution of a population, the distribution of a sample, and the sampling distribution of a statistic. I know they all sound the same, but they're actually three different things. Determine whether or not a statistic is an unbiased estimator of a population parameter, and describe the relationship between the sample size and the variability of a statistic. Inferential statistics helps investigators draw conclusions about a population based on a sample drawn from that population. Since not every sample, no matter how carefully selected, may be truly representative of the population, there are risks involved in inference techniques. Probability can be used to quantify those risks. First, we have to understand something about sample statistics and how they behave. Estimation using a single sample. One of the primary jobs of a statistician is to estimate characteristics of populations. What proportion of students drive to school? What is the average weight of a teenager? To make these estimates, statisticians will select a sample from the population of interest and study the members of the sample. Think about back in chapters 4 when we were talking about good sampling techniques. Hopefully this sample is a simple random sample or a random sample of some sort, and that there's no bias created when sampling. A parameter, so back it up a second, a sample has statistics. Whatever you pull from that sample is labeled a statistic. A parameter is a fixed number that describes the population. So parameter starts with P, and it comes from the population, which also starts with P. What statisticians are interested in estimating. For example, the mean height of a woman is 62.5 inches. So what this is saying is that we can't know exactly what the mean height of a woman is in the whole world. That's impossible. But we can draw several random samples and estimate what it might be. Let's talk about some symbols. They like to use the Greek. We've talked about this one before. It's called mu. It's the funny looking U with the tail. And it is the mean of the population. Type of variable, meaning is it categorical or quantitative? Well, think about how do you get a mean? Do you need numbers or percentages? It's going to be quantitative. Next, we have this funny looking O thingy, sigma. It's the standard deviation of your population. The type of variable, again for now, it's just quantitative. Sometimes they'll use the symbol for categorical as well, but we'll talk about that later. When they have a lowercase p, and there's no little hat on it, that represents the proportion of the population that we're interested in. So now all of a sudden we're talking about proportions and not averages. We've switched to categorical variables. A proportion, usually think of a yes and no question. How many people said yes to the answer, do you like cheese pizza? And how many people said no? It's a proportion. So we're switching to categorical here. In other words, we can estimate things about our population using either quantitative variables or categorical. Parameters are generally unknown, which is why we need to estimate their value. And it's what the world wants to know. It's what your politicians want to know. It's what all the big bosses want to know. They want to know exactly what it is, but it's impossible to know. So they call in the statisticians and they estimate the value. Wonderful world of statistics. So now a statistic is a number that describes the sample. Again, just like I said earlier, this one starts with an S, and so does statistic. It's what statisticians use to estimate the parameter. For example, 22% of students interviewed prefer starting school at 7:40. I know a lot of you would probably prefer starting at maybe 10 in the morning and getting out by noon. That would be nice. So, symbol X with a bar over it. I usually call it X bar, and that's how many other people would refer to it. That is the mean of the sample. Type of variable, whenever we talk about averages again, yep, it has to be quantitative. Lowercase s, that is your standard deviation. Uh-oh, might need to recalibrate here. Trying to hold on to it. Standard deviation of your sample. And again, this is still going to be quantitative. Now we've got our lowercase p, but it's wearing that little hat, meaning it's not the true value, it's an estimate. So that is the proportion that we're interested in of the sample. Think of it as being in disguise. It's got a hat on it. Type of variable, yes, we're switching back to categorical for this one. Do all samples yield the same statistics? Of course not. There are an infinite number of samples you could usually take in any given situation. Okay, well, no, not infinite, but there's several possible ones that you could possibly take. So, when you have all these different samples that are possible and all these different statistics that come with them, we get sampling variability. It occurs when the value of a statistic varies in repeated samples. So it's important that estimates are constructed in such a way that also conveys information about the anticipated accuracy of the estimate. Sampling variability is sometimes called sampling error. And that is what you may get caught up on when you're reading multiple choice questions. Is that sampling error is referred to as our sampling variability. In other words, if I take a random sample at South River High School of the number of students that like pepperoni pizza, and maybe I take a random sample of 100 and there's 2,300 in the school. I take one random sample, I find 60% like pepperoni pizza. Take another random sample, I find 40% like pepperoni pizza. I can go on and on and on. The fact that I'm getting 0.6 for my first one, 0.4 for my second one, maybe 0.25, and then maybe 100% like pepperoni pizza. Those are all varying. That's your sampling variability. Eventually, over time, the larger my sample size and the more samples I take, it'll narrow down to the true value. If we have time, we'll do an example with poker chips in class. Next. In general, there are two types of estimates that can be made. There's a point estimate and an interval estimate. Don't know what that was. Definition: a point estimate is a single number that represents a plausible value for the population characteristic. It's called a point estimate because it represents a single point on the number line. So if I just take one sample and I get one value, that would be that point estimate. For example, based on a recent survey, 61% preferred chocolate ice cream. The census showed 54% preferred chocolate. So our parameter is a census because remember, a census is when you ask everyone in your population, which, yes, is usually impossible unless you have a controlled population. So the parameter here would be our 54%. Oh. The statistic comes from that sample. In a recent survey, 61%. Didn't tell us how big it was, but that's okay. And since we're talking about percentages, those are like proportions. You just move the decimal over. So your P from the population parameter is going to be 0.54. And the P hat, in this case, is 0.61. Later, we'll talk about how far off that is and if the difference is big enough to say that maybe the proportion has changed. Maybe, in fact, more people are starting to like chocolate ice cream because they hear it's good for your heart. No idea. An interval estimate is a range of plausible values for the characteristic. It's called an interval because it represents an interval on the number line. For example, based on a recent survey, we estimate that between 58% and 64% of Democrats support Jerry Abersom. Yeah, 61% plus or minus 3%. Which statistics should we use to make a point estimate? Oh, back it up. Eventually, we'll get into this, and they've got a nice little name called confidence intervals. And we're going to be guessing at what the true value might be and saying how confident we are that the true value falls in a particular range. Which statistic should we use to make a point estimate? There are two things to look at for when choosing a statistic to estimate a population. The statistic should have no bias and low variability. Well, that's your ideal world. Of course, you don't want bias. That messes things up. And low variability, meaning each sample that you take, the values you get are real close together. An unbiased statistic is a statistic with a mean value equal to that of the population characteristic being estimated. It's centered in the right place. So your statistic, whatever you're going to get, is exactly what the population value is. So unbiased statistic could be when X bar actually equals your mu, or if we're talking proportions and categorical variables, when P hat is actually the same as your P. Now, in the ideal world, of course, life's not perfect. That's not going to happen. But the closer it is to equaling it, the closer it is to being an unbiased statistic. For example, some unbiased statistics, we have our median, mean, and proportion. Of course, median and the mean is usually better when your data is symmetric. They're unbiased since their sampling distributions were centered in the right place. Some examples of biased statistics would be range and max. Why would these be biased? Well, what's the range getting the maximum values possibly going to involve? It could also be your minimum. They could involve possible outliers. And they're only talking about one end of the curve if you're considering your max. Given a choice between several unbiased statistics, which one should we use? Why? Well, everything's going to boil down to our lovely mean value, which for quantitative data, that's going to be quantitative mu, and for categorical data, it's actually going to be P. It's the one in the middle. And so let's back it up just a second and go back to these two. The proportion of your population. This is also considered to be the mean in certain cases. I just like the word mean better. but everything's going to fall back to our lovely normal curve. So, sampling distribution of a statistic is the distribution of the values of that statistic in all possible samples of the same size taken from a population. It's an ideal distribution based on probabilities. So this is that word that people tend to get hung up on, not just a word, it's a term, phrase. It usually could be represented in a table or a graph. Or graph. And again, we'll go through an example with poker chips and also with pennies in class. But it's just a picture of all the possible statistics you could possibly get. If I took several random samples of 100 students at South River High School, and I found that in one sample of 100 students, I found that, let's put this as 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. Let's say that I found 2 of those samples, and 2 of them 20% like pepperoni pizza. Well, in 4 of them, 30% like pepperoni pizza. And then in 1 of them, 40% like pepperoni pizza, and so on. It's going to be a picture of all your possible outcomes with your frequency over on your y-axis, or it could be represented as a table. Let's go back up to this last part here. As statisticians, we can now look at sample results and reach important decisions. We may decide that the results are within a reasonable margin of variation from what we expected, or we may deem our results to be so unlikely that we don't believe they could simply be due to sampling error. If this is the case, we can call it statistically significant. In the next section, we'll learn how to make that distinction. We used to focus on a parameter, derive a statistic from it. Now we're going to focus on the statistic itself. The sample proportion or mean becomes our datum. In our imaginations, we compare it to all other possible values we might have obtained from all other samples we might have taken. So we're actually going to start looking at an estimate interval. So what I would like you to do now that we went through these notes on this first section is take a look at section 7.1 and read pages 422 to 436. And if you're at home enjoying your snow day right now, you don't have your reading guide. So I suggest you just take notes. Do old-fashioned outline form. Take notes on what you read. And you can also start looking at these 4 problems out of the book. Page 439, 15, 17, 21, and 23. I will post the agenda on Edmodo along with these notes so that you have them to fill in. And thank you, and hopefully this comes out successful. Enjoy your snow day.